Hello, welcome to Automata on Oddly Shaped Words. My previous video series, Regular Languages and Model Theory, was in part a celebration of the wide variety of ways of categorizing the regular languages. The big ones being that we could describe regular languages in terms of deterministic finite state automata, non-deterministic finite state automata, regular expressions, and there was also a translation to the weak monadic second-order theory of one successor. And in mathematics, whenever you have lots of different perspectives on the same thing, you can, by switching back and forth between different perspectives, prove a whole bunch of things really easily. What's inspired this video series is that we can generalize these equivalences to various other notions of word. And what do I mean by that? Well, we can imagine a word as a linear collection of points where these points have been labeled by characters from some finite alphabet. And so we can talk about oddly shaped words as other collections of points with different structures on them, and we're labeling each of the points with a character from a finite alphabet. For instance, we could take a finite tree and label all of its nodes with characters from a finite alphabet. We could also take a collection of points corresponding to the natural numbers and label all of those points with characters from a finite alphabet. This gives us words that are an infinite sequence of characters. And we can also take infinite trees and label all of their nodes with characters from a finite alphabet. In each of these three cases, we can make sense of deterministic finite state automata, non-deterministic finite state automata, regular expressions, and a corresponding monadic second-order theory. And by making the right choices, we can have all of these describe the same collection of languages. A notion of regular languages for these various odd shapes for words. In this video series, I also hope to talk about some other notions of word. We could, for instance, take a finite graph and label all of its nodes with characters from some finite alphabet. In this case, the equivalences are not so nice, but there are a number of interesting positive and negative results and some open questions, and I'll talk about all of those. I also hope to use this video series as an excuse to do some literature research on notions of automata on arbitrary linear orderings and automata on continua. So for instance, we could imagine taking all of the points in a linear ordering and labeling them with characters from some finite alphabet, or we could imagine taking all of the points in the interval from 0 to 1 and labeling them with characters from some finite alphabet. But to start this video series off, I'd like to talk about binary tree automata. Here, when I'm talking about binary trees, I'm talking about finite, rooted, ordered, and of course labeled trees. So for some reason in mathematics and computer science, we like to draw our trees upside down. And at the top of the tree, we have a node that's called the root, and all of the tree kind of branches off out of that root. Each node can, but doesn't have to, have a left child and a right child. So the node that's immediately below another node to the left is called the left child, and the node that's immediately below a node to the right is called the right child. And we make a strong distinction between these two. Even though this node here only has a left child, we want to distinguish that from this node only having a right child. This node only has a right child and doesn't have a left child. This node only has a left child and doesn't have a right child. And of course, not every node has to have children. This node here and these nodes here don't have any children, and so they're called leaves. For each node, we can talk about the subtree corresponding to that node. So for instance, for this node here, the subtree corresponding to this node is going to be the set of all points below it. And that's going to be a subtree of the original tree. And for instance, the subtree corresponding to this node here is just these 3 points here. The key idea with binary trees is that we want every single node to correspond to a series of L's and R's, describing the sequence of operations either going to the left child or going to the right child, to get us there from the root. So the root corresponds to the empty sequence of L's and R's because we're already at the root. But to get to this node, we go to the left child, and then to the right child. So this node corresponds to the sequence LLR. To get to this node, we take the right child and then the left child. So this corresponds to the sequence RL. And again, we're going to want to label all of the points of the tree with characters from some finite alphabet. There are various different ways of thinking about deterministic finite state automata, and some of them are more or less useful when it comes to generalizing to these new notions of automata on oddly shaped words. And I think the best way of generalizing this is actually to show you what it looks like to run a deterministic finite automaton on a word when we view that word as a unary tree. So if we have a word, we can view it as a unary tree. And for some reason, we're going to want to view this also upside down, where the end of the word corresponds to the root and the start of the word corresponds to the leaf. This here is a unary tree. Each node has at most one child. And to run a deterministic finite state automaton through it, well, we want to start off in the start state, and then we want to apply our transition function for A to work out what the state is after reading the A. And then after that we read a B, which is going to apply the transition function for B. Here I'm using a down arrow to indicate that we're going to take this and plug it into the transition function here to work out what state we should be in here between these two B's. So typically when we think of finite automata, we want to think of the states as occurring halfway between the input characters. When we read an input character, we switch from one state to another. We're going to want to move everything half a step over so that the states wind up lining up with the input characters. In this case, we can still make sense of having states kind of in between the input characters on these various edges, but in the long run, it's just going to make sense to move the states to be where the input characters are, the various nodes of our structure. At each step, we apply our transition function to the state appearing below and the character that we read at that particular point. And when we make it to the end of the word, when we make it to the root of this tree, hopefully this state will be in our acceptable set of final states. So this is the perspective on finite state automata that I'm going to want to take when generalizing to trees. We're going to start at the leaves and work our way towards the root, figuring out what state we want to associate to each node, and hoping that we wind up associating a final or accept state to the root node. So a deterministic finite state leaf to root binary tree automaton, which I'll just call a deterministic binary tree automaton, is a tuple. Again, we're going to have a finite alphabet, a finite set of states, some sort of transition function, and a set of final states. Again, we're going to want to associate states to all of the nodes of this tree, starting at the leaves. And we're going to start off by looking up what states to associate to the leaves by calculating delta of octothorpe, octothorpe, C. So delta, the transition function, is going to take in three inputs. It's going to take in two states, which could also be octothorpes, and it's going to take in a character from the alphabet. And it's going to output a state. And when we're interested in figuring out what state to associate to a leaf node, we're going to input octothorpes to indicate that there are no left children and there are no right children for that particular node, and we're going to input the character that we see at that node. So let's say that we have a specific tree automaton where delta of octothorpe A is equal to 1, and delta of octothorpe B is equal to 0, where let's say our set of states is the set containing 0 and 1. So this tells us that anytime we see a leaf that has a B associated to it, we want to give it the state 0, and anytime we see a leaf that has an A associated to it, we want to give it a 1. And then we're going to work our way up the tree. If we see a node with character C whose children have been associated the states Q left and Q right, then we will calculate the state for this node here by looking up delta of Q left, Q right, and C. So for instance, let's say that delta of 0, 1A is equal to 0. Then that means that because this node has symbol A and has a left child that we associated the state 0 to, and a right child that we associated the state 1 to, we're going to associate the state 0 to this node here. In the case where we have a node that doesn't have a left child, we're going to put an octothorpe as an input to the transition function, and just input the state associated to the right child and the symbol at that particular node. So in order to figure out what state to associate to this node here, we're going to want to look up delta of octothorpe 0A. No left child, the right child gets state 0, the node itself has state A. And let's say that this is equal to 1 for this particular function here. That means that we'll associate the state 1 to this node here. And the reverse, if we only have a left child and no right child, we're going to want to put an octothorpe in the position for the right child when calculating the state for this node here. And then finally, to calculate the state for this node here, we want to input the states of its children and the character at that node. So we'll associate a 0 to this node here. So that's how we calculate the run of this automaton, that is an association of states to all of the positions. And finally, we just have to check if we wind up associating an accept state to the root. For this particular automaton, unfortunately, the set of accept states is just the set containing the state 1, so this automaton rejects the input that we had. It's really helpful to go through some examples on your own, so I'll give you a moment to pause the video and try to work out what happens if we run these particular trees through this particular automaton. What states do we associate to each of the nodes? That is, what does the run look like? And do we wind up accepting or rejecting? And for a slightly more advanced challenge, can you work out what this automaton tells us about a particular tree? So here's what the runs look like. The first and last trees are accepted and the middle tree is rejected. And ultimately this automaton accepts a tree word if there are an odd number of A's in that tree. So why do we care about finite tree automata? Well, again, the reason I'm interested in finite tree automata is because I'm interested in the weak monadic second-order theory of two successors. But finite tree automata also capture a really important notion of computation. Suppose that we have some sort of arithmetical expression. If we want to evaluate this on a computer, we're first going to want to turn it into a tree. Trees are the natural data structure for storing and processing mathematical expressions. This is called an abstract syntax tree, and it captures the order of operations of the expression. We're first taking 2 and 3 and multiplying them together, and then we're taking 5 and adding it to the result of that product. And so if we want to evaluate this tree, evaluate the arithmetical expression corresponding to it, we want to start at the leaves and work our way towards the root, assigning a number to each of the nodes corresponding to the value of the sub-expression for that subtree. So each of the leaves gets associated to the number in that leaf. And then if we have a product node, we're going to look at the numbers, states as they were, of the children nodes and take their product. And that will give us the number, the state that we're associating to that node. And then when we want to evaluate this node, we look at the states associated to each of the child nodes and take their sum. And then the state, the number associated to the root node, is the value of the entire expression. Now, this example here doesn't correspond to a finite state automaton because there are infinitely many possible states that we could be associating to each node. There are infinitely many numbers. But we can fix this either by considering modular arithmetic, or we could, for instance, be looking at Boolean arithmetic with true and false and ands and ors, things like that. But the idea behind the computation of starting at the leaves and working towards the root, where we can work out the thing that we want to associate to each node by looking at what's at that node and what we've associated to each of its child nodes, that is the essence of a deterministic binary tree automaton. More generally speaking, these tree automata capture recursive processes on trees. Here I have some example pseudocode that evaluates the value of a tree. In order to evaluate our function on a particular tree, if the root of that tree has children, we're going to want to evaluate that function on the children. We're going to want to take the subtrees corresponding to the children and evaluate the function on those first. And then, based on the symbol that we see at our node and the values that we got from calling our function recursively, we will compute a value to be associated to the entire tree. Eventually, these recursive function calls will work their way all the way to the leaves, and we have a way of evaluating trees that only consist of one node, subtrees of our original tree that corresponded to leaves. So, thanks for watching. In the next video, you might be curious if there's a way of making sense of automata that start at the root and work their way towards the leaves. These are called deterministic root-to-leaf tree automata, and I also hope to talk about non-deterministic tree automata. I hope that you'll join me for that. In the meantime, if you have any questions or comments, please leave them down below, and be kind to each other.